Yeah, good morning everyone. So today is the summary class and last class. So I will go through every lecture what I taught 12 lectures. So then so then after that we will finish the class. So today is just a summary session. Uh, so in the first class I talked about vector space. What is the vector space? Vector space is a set of all the vectors if these two conditions are satisfied. One is this x, if x and y belong to a vector space V, then x plus y should also belong to V, and scaling condition should also be satisfied. If x belongs to V, then CF should belong to V, where C is a scalar which is taken from a field F, which can be a real number you can take. So then what are the subspace? Subspace is just a set of subset of vector space. And then linear independence vectors. What is the linear independent vectors? So if n number of vectors, there are n number of vectors v1 to vn. They are said to be linearly independent if summation ci bi is equal to 0 gives the solution all ci equals to 0 for all values of I. Then for a matrix there are four kind of space vector space are there. One is range space or column space, row space, null space, and left null space. So for the range space, that is the column space. Column space is just a set of all the vectors y such that y is equal to ax for all values of x. Okay, so that is the range space. So that means it's just a span of all the columns of a matrix. That means the span means just a linear combination. This summation CIVI is written right in linear independence definition. That is the span actually. So it's just a span of all the columns of a matrix is called the range space of that matrix, and null space also. Null space is just set of all the vectors x such that ax equal to 0. So if vector x satisfy ax equal to 0, then that x belongs to null space. And then row space is just span of all the rows of a matrix or span of all the columns of the transpose of a matrix, transpose of the matrix. So that is the row space. Then the left null space, it's just a null space of a transpose. So this is the rank nullity theorem. So where this for a matrix to be and nodes. Okay, kindly post this class video and notes in Anvil portal. Yeah, sure. I will post. Sorry, last day I didn't post. I will post everything today so that you can prepare. Okay. So this is the this is the rank nullity theorem. So for a matrix of dimension m cross n, so for the m dimensional space, that is the r power m. For the m dimensional space, there is a space called subspace called range space, and there is also another subspace called left null space. That is the null space of A transpose. So both are in the vector space of R power m or m dimensional vector space. But the dimension of the range space of a matrix is equal to R. Suppose there are the matrix is of dimension m cross n. So there are n number of columns are there. So out of n, only R number of columns are linearly independent. So then the dimension or rank of that matrix is equal to R. And then m minus r number of linearly independent vectors are also there in the m dimensional space. So m dimensional space means there are m number of linearly independent vectors, or they are called the basis of the vector space. So only R contains in the range space and M minus R will contain in the null space of A transpose. That is the rank nullity theorem. So that means M is equal to dimension of range space of A plus dimension of null space of A transpose. So this is the rank nullity theorem. Similarly, n is equal to dimension of range space of a matrix plus dimension of null space of a matrix. So that is a rank nullity theorem. So these are the eigenvalue and eigenvectors definition. So x and lambda are said to be eigenvector and eigenvalue pair if ax equal to lambda x, where x should not be zero. So there is an eigenvalue and eigenvector definition, and how to find out the eigenvalues. Determinant of a minus lambda is equal to zero, and if you solve these equations, then you will get the eigenvalues. So these are the norms and inner products. So just a definition of norm. So a function which goes from a vector space to a real numbers or real field. So if this for so that function is called to be a norm if these three conditions are satisfied. One is non-negativity, that is norm of x is greater than equal to zero, and that is equal to zero only when x is equal to zero. So when there is a zero vector, there should be the norm should be zero. Otherwise, it is non-negative. It is positive. So Cx, if C is a scalar, then norm of Cx is equal to mod of C into norm of x. And triangle inequality is also there. Norm of x plus y is less than equal to norm of x plus norm of y. So this is the definition of LP norm, where P goes from 1 to infinite. Okay, so this is the definition of LP norm. But L0 norm is called is a norm also. So it's not a norm, but it's called a norm. L0 norm means just number of non-zero elements in a vector. So that will be talked about later. So then inner product is just so inner product is also a function which goes from two vector space to real numbers. Then inner product of x comma x, that means inner product of a vector to itself is always greater than equal to zero. That is the non-negativity, and it is equal to zero when the vector is also zero. Vector itself is zero. So then x so then the second condition is inner product of x comma y plus z is equal to inner product of x comma y plus inner product of x comma z, and then inner product of cx comma y is equal to c into inner product of x comma y, and inner product of x comma y is equal to inner product of y comma x conjugate. So if you check y transpose x is also inner product, you can see that you can show that these four conditions are satisfied. So y transpose x is also inner product. This is okay. So the sample problems are so there was a matrix. We need to find out the Hermitian of a matrix. Hermitian of a matrix means conjugate transpose. So we need to find out the transpose. Then we will do conjugate of every elements. So that is done here. Then there are two vectors. So we need to show that are they orthogonal or not. So orthogonal means oh, the first question is, are they linearly independent or not? So for the linearly independent, we need to find out summation. We need to solve the equation summation of Ci xi is equal to zero, and see that what is the solution of that equation. So here summation Ci xi is equal to zero. That gives the solution all Ci is equal to zero for all values of I. So that means x1 and x2 are linearly independent. Now we need to show that are they orthogonal or not. Orthogonal means y transpose x should also be zero. So that is not equal to zero. That is coming as one. So that means they are not orthogonal, but they are linearly independent. And so there are also similarly one other question. And then there is a matrix. We need to find out the eigenvalue and eigenvector of that matrix. So just solution of determinant of a minus lambda is equal to zero will give the eigenvalues, and then putting those eigenvalues in the equation ax equal to lambda x, we will get the eigenvectors. So that is very simple process to find out eigenvalues and eigenvectors. So then, if A is a Hermitian matrix, then A Hermitian is equal to A. That will give the all the eigenvalues real. So that proof is here. Okay. So I'm not going through the proof. So I'm just giving the summary. So then there is a vector. Then we need to find out the L1 norm and L2 norm. The definition is same actually. So for the LP norm, when C is greater than equal to 1, so we have the definition of the norm, the formula of the norm is that LP norm summation of, uh, here it's written right above. Yeah, the summation of mod of xi power p whole power 1 by p. So that is the LP norm definition. So just taking p equals to 1 will give the L1 norm, and then p equals to 2 will give the L2 norm. Taken. Yeah, so these are the L1 and L2 norm. So which is giving L1 norm is equal to 1 is just summation of all the values, mod of absolute values actually. So then it's giving n, and then L2 norm is equal to root n. So similarly, one other question we need to find out L1 and L2 norm, same approach. Then yeah, so this is the random variable. So for the x, for x, suppose x is a random variable which is satisfying distribution of normal distribution, standard no, only normal distribution of mean mu and variance sigma square. So the distribution is formula is this 1 by root 2 pi sigma square e power minus of x minus mu square by 2 sigma. This is just a formula for the normal distribution or Gaussian distribution. Then for the so then we can find out standard normal distribution is y equal to x minus mu by sigma. So which will have mean 0 and variance 1. So there is a standard normal distribution. And then there is a matrix A transpose A which is positive semi-definite. No, we need to show that it's a positive semi-definite. So A transpose A is a positive semi-definite matrix. It's shown here. X transpose A transpose AX is greater than equal to 0 always. That is the positive definition. So then, uh, uh, yeah, that is the question. And A transpose is also a positive semi-definite. So yeah, that is the first lecture. Then we can go to the second lecture. So, so this is the Gram-Schmidt process of orthogonalization. That means, suppose there are linearly independent vectors. There are n number of linearly independent vectors, but they are not orthogonal. So you can find out n number of orthogonal vectors from the n number of linearly independent vectors. How to find out? Oh, we need to follow Gram-Schmidt process of orthogonalization. So in the first so in that process, at first suppose there are inputs are x1 to xn which are linearly independent vectors, and outputs are z1 to zn which will be orthogonal vectors. So then so at the first step we need to take y1 another vector is equal to x1, and z1 is equal to just y1 by norm of y1, because the orthonormal vectors the norm is unit, they're a unit norm. That's why so this z1, if you take the norm of z1 is equal to norm of y1 divided by norm of y1, so that is equal to 1. So that's why this z1 is equal to y1 divided by y1. So one orthogonal vector you found out already from the first process. So then in the second uh, there so in the second process you will need to do y2 is equal to x2 minus inner product of x2 comma z1 into z1. So that means you have to subtract the portion of x2 on z1 from x2 itself. Okay, because z1 you have already found out, so now you just need to subtract those portion. So then this z2 also you found out, z2 is equals to y2 divided by norm of y2. Similarly for yi, for the ith number of orthonormal vector, yi is equal to xi minus, you have to subtract all the portion of xi on z1 z2 dot dot up to zi minus 1. Okay, so that is done here. So xi minus summation n equals to 1 to I minus 1 inner product of xi comma zn inner product of xi comma uh, uh, sorry yeah, xi comma zn into zn. So that is done here. So then zi equals to yi divided by norm of yi. So this is just one example. you need to there are three linearly independent vectors. Just you need to find out the orthonormal vectors from these three linearly independent vectors. So this is the process. At first process, we will take x1 equal to y1 itself, and then we will find out the z1 equals to y1 divided by norm of y1. That is done here. 1 by root 3, 1 by root 3, 1 by root 3, 0. Then x2 comma z1 inner product I have found out, that is equal to root 3. Then y2 is equals to x2 minus inner product of x2 comma z1 into z1. So that is that is giving y2 is equal to minus 1 1 0 1. Then norm of y2 is equals to root 3. So then z2 is equals to minus 1 by root 3, 1 by root 3, 0 1 by root 3. Then in the third step, you need to find out norm of x, sorry, inner product of x3 comma z1 and inner product of x3 comma z2. Both we have calculated, then subtracted those portions. Then ultimately we are getting y3 is equal to 1 1 minus 2 0. Then norm of y3 is equals to root 6. Then z3 is equal to 1 by root 6, 1 by root 6 minus 2 by root 6 and 0. Okay. So these are the orthonormal vectors. So then one other thing is that for a matrix which have linearly independent columns, so that those columns you can convert those columns to orthonormal columns also through this Gram-Smith process of orthonormalization, and then that matrix you can write down as a keyword decomposition where this Q is the those ortho. So one second, yeah, Q will contain those orthonormal vectors, and R will be a diagonal upper triangular matrix. Sorry, upper triangular matrix. So which is for this case it's shown here. So A is equal to this. Z1, Z2, Z3 in the Q matrix itself are the orthonormal vectors, and this R is just a upper triangular matrix. Uh, then for similar matrices, so a matrix B is said to be a matrix B is said to be similar to the matrix A. So actually, this definition dimensions should be uh, one second. It should be square matrix. So this dimension should not be rectangular. So it's written wrong. So A B should be a some square matrix n cross n, and A should also be a n cross n matrix. So okay. So only for the singular value decomposition we should have. I mean we can have rectangular matrix, but for this similar matrix that is only applicable for the square matrix. So it's written wrong. Only square matrix should be there. So for a matrix B is said to be similar to the matrix A if this B is equal to S inverse sigma S, where sigma is a diagonal matrix. Okay, so that is the definition. And unitary matrix is that this U is the unitary matrix if U Hermitian U is equal to U Hermitian is equal to identity matrix. So that means its inverse is also its Hermitian is its Hermitian, and norm of UX equal to norm of X. Then normal matrix definition is just definitions. So A is the normal matrix if A Hermitian A is equal to A Hermitian. So these are the okay. So these are the matrix inversion lemma. So A plus U C V inverse is equal to A inverse minus A inverse U C into C inverse plus V A inverse U whole inverse V A inverse. So so this the proof if you want. So then you can just multiply this right hand side, this A inverse minus all those things into A plus U C V, and check it that is it giving correct or not. But yeah, this is the matrix inversion lemma actually. So and A inverse would also exist. So for this lemma to be satisfied, A inverse would exist and C inverse would exist, and C inverse plus V A inverse U whole inverse would also exist. So these three inverse should exist. So then if you put C is equal to 1, and this U and V is just a column and row vectors respectively, and A is an identity matrix, then you will get this I plus UV transpose inverse is equal to I minus UV transpose divided by 1 plus V transpose U. And you can check that the determinant of this I plus UV transpose is equal to itself 1 plus V transpose U. Okay. So then convex function. So now we are so these are up to, I mean, up to this we deal about linear algebra. Now we are going to optimization. So their convex function definition is a function fx is said to be convex function for if this for all values of x and y, those are two vectors, and if this theta x, f of theta x plus 1 minus theta y is less than equal to theta fx plus 1 minus theta fy, where theta belongs to I mean theta goes from 0 to 1 itself. So theta is 0 less than equal to theta less than equal to 1. So then we can say f of x is a convex function. And there are two other ways also to check a function to be convex or not. That is a double derivative. So that is also we'll talk about later. So now convex set is set omega is called convex set if we have tx plus 1 minus ty belongs to omega. If x so suppose the x and y belongs to omega, then tx plus 1 minus ty should also belong to omega, where t goes from 0 to 1. So that means in geometrical or in physically, suppose there are 2 points belong to set omega. Then if you join those 2 points, those whole lines should also belong to that set omega. That is that physical definition. So then convex optimization problem. A problem is said a optimization problem is said to be convex optimization problem if the objective function is convex as well as the constant set is also a convex set. So then we can say that the optimization problem is the convex optimization problem. Then affine set is just the definition is same, but here t will be for so t is t can be any real number. So that is the affine set definition. So then so this is just a one sample problem. Just I have given one matrix, then I have shown that how to find out the linear and independent columns. Okay, before that, the rank of a matrix is equal to maximum number of linearly independent columns. Correct. Yes, and then so then okay, so then how to find out the row reduced echelon form? So that is uh, that will give the rank of a matrix. So this is actually okay. So this is done. So this rank is already there 3, but for the row reduced echelon form, we need to show that above this pivot 2 in the second column should also be 0. That is, this 2 also should be 0. One is asking. Explain the difference between convex and quasi-convex. Okay. Okay. So then this multivariate distribution. So multivariable, for the multivariable case, if there is a random vector, then there will be a distribution. So this is how to find out the distribution, that is written here. So then suppose there is a matrix A, then uh, uh, how to find the basis of four fundamental subspaces. So that is it's a very lengthy process, so that is done here. So then trace of this thing, trace of AXX Hermitian is equal to lambda into X Hermitian X, where lambda is just a eigenvalue and X is eigenvector. So consider the minimization problem fx. Then how to show that is a convex function. So for to show a convex function, we have a double derivative constant. So that we'll talk later actually. So then is the constant set is convex set. So that is done. That is proved from the basic principle that tx plus 1 minus ty belongs to omega. So that is done here. Then so this is the determinant of I plus CD transpose. I told that I plus UV transpose, determinant of that is equal to 1 plus V transpose U. So that is proof is here, 1 plus D transpose C. So then okay, this is done. So then in the third lecture, so norm ball. So these are just definitions of some optimization uh, constants. So for the norm balls, so this is the definition of norm ball. Then ellipsoid, then norm cone. polyhedra, and then okay, this is the LP norm definition. Infinite norm, how to how if you put p equals to infinite, then how will get that LP norm, L infinite norm is equal to, sorry, L infinite norm is equal to uh, maximum of absolute value. One second, infinite norm is equal to maximum absolute value. Then so L1 norm ball is yeah. So L1 norm ball is a tilted square, and L2 norm ball is just a circle, and L infinite norm ball is a square itself. So these are sample problems of how to find out the A inverse, where A is equal to this I plus CD transpose. So this is just putting those formula here. So then I minus AB determinant is equal to I minus BA determinant, where A and B both are square matrices. So that is shown here. Proof is shown here. And if I minus AB is invertible, then I minus BA will also be invertible, and vice versa. So that is proof is also shown here. Then rank of this, how to find out rank of this. So then find the basis of so the same question. Then so this is which this should be, so this is a seven question, the answer should be a convex cone from the definition. Okay, so then singular value decomposition is just one topic, so that will be helpful for later application. So for a rectangular matrix A rank of A is equal to R. Then that matrix will have R number of non-zero singular values, and singular values are the root of our eigenvalues of A Hermitian A. So and then if sigma 1 is greater than equal to sigma 2 dot 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 greater than equal to sigma R, then we can write down U Hermitian AB is equal to a diagonal matrix, where this sigma will to contain the structure of sigma should be D00, where D is a R cross or diagonal matrix, which will take sigma 1 to sigma R as its diagonal elements. So these are the one application that will be help apply. So one application is in the orthogonal frequency division multiplexing, OFDM. So then the week three, then for the week four. So L0 norm. What is the difference of L0 norm? L0 norm is just a number of non-zero elements. So for this vector, we need to find out the L0 norm. That means we need to calculate the how many non-zero elements are there. Okay, then important properties. So okay, so then there are some important properties professor taught in the class. So AB is similar to BA; those properties are there. So then, uh, yeah, x1 norm is less than equal to root n x2 norm, where n is the dimension of the vector, and x2 norm is greater than equal to x infinite norm. So and x1 norm is greater than equal to x2 norm. So that means x1 norm is greater than equal to x2 norm is greater than equal to x infinite norm always. So x is a random variable. Then expectation of x. So this is the convex set. So okay, then convex function definition is also talked about once again. And these are the convexity checks. So this checking we are is talking about. So this is the for the scalar case we need to find out the double derivative, and that should be greater than equal to 0 for the function fx to be convex function. And for the vector case we need to find out the gradient and then Hessian of that function. So that means the double derivative for the single for the scalar case. So if the Hessian is positive semi-definite, then we can say that this function fx is a convex function, where x is a vector. For the vector case, this is the definition. And this is a least square problem. So least square problem is so y equal to hx plus n. So least square problem is that minimizing the distance between y minus y and hx. So that means minimizing y minus hx norm square. So the solution is given as x is equal x hat is equal to h Hermitian h inverse h Hermitian y, where h Hermitian h is invertible. So this itself is called the pseudo inverse of h. So that means pseudo inverse h of h is equal to h Hermitian h inverse h Hermitian. So then sample problem. So this is the norm cone. Then L infinite norm ball of the set two dimensional square is a square. So that is square. So then upspace okay, so yeah, so this for the seventh question. So we need to show that this is this a convex function or not. That means we need to show that this we need to find out the Hessian and show that it's a positive semi-definite. So that is done here. We have found out the Hessian and this is the positive semi-definite if tau is greater than equal to 0. If tau is greater than equal to 0, then these diagonal elements will also be greater than equal to 0. That means the function is the matrix is positive semi-definite or positive definite it is greater than 0. So then consider the optimization problem. This then okay, it is a convex optimization problem. Yeah, so for this case, so we need to show that this set omega is a convex set. So the checking is just we will solve it from the basic. So that is we consider two vectors x and y that belongs to omega. Then we'll show that t x plus 1 minus t y, where t is from 0 to 1, will also belong to omega. So that is done here. Then Markov's inequality is proof is there, so it is so that's a proof. Then Chebyshev's inequality and Jensen's inequality are talked about here. So you can get short questions in the exam. So then what is this Jensen's inequality fx? Okay. Then qx. So so this is the Q function. So Qx is just for the standard normal distribution. Minus if x will go from minus infinity to plus infinity. But if you take x to infinite, those portion, if you find out the area of those portion, that will give the Qx actually. So for the standard normal distribution. So that is Qx is a convex function and how so as this q double dash x is greater than equal to 0, um, then q of root x is also a convex function. Then so that is shown here. And then fx is a convex function, then alpha fx. So these are the some properties. Fx, if fx is a convex function, then alpha fx plus c for alpha greater than equal to 0 is also a convex function. If ix is convex, so if there are n number of convex functions, their linear combinations will also be a convex function. Non-linear combination, the summation will also be a convex function. Yeah, then positive linear combination will be convex function because alpha fx, if alpha greater than equal to 0, will also be a convex function. So then if fx is a convex function, then f of ax plus b is the affine function. There is also ax plus b affine function. So then that is also a convex function. So that is all the properties. Then conjugate function is that if fx is a convex function, then f star of y is equal to maximum of y transpose x minus fx, maximum with respect to x. So this is the always convex even if fx is non-convex. So this is the conjugate function. So there is a function fx, but fx is not a convex function. So we need to find out some other function which is convex function from the fx. So that is shown here. Maximum of y transpose x minus fx, that is the convex function. Um, so then quasi-convexity that is that f is quasi-convex if there is a set s of t st that is equal to x, which will take I mean for all values of x such that f of x is less than equal to t. So is convex. So this set is a convex set. So yeah, so this is the definition of quasi-convexity. Uh, yeah. So that means the definition of quasi-convexity is that suppose there is a function f, uh, and there is another set we need to find out, that is the s of t, that is equal to for, which will take all the values of x such that f of x is less than equal to t. If s of t is a convex, s of st is convex set, then we can say that f is a quasi-convex function. This is quasi-convexity definition. So there are some sample problems. The function x cube, that is a convex function for x greater than equal to 0, and concave function for x less than 0. So that is shown here. Then q of x is this thing. Then q dash and q double dash of x. What are the values of q dash x and q double dash x? Those are shown. Just uh, professor has already taught. Yeah, so then after that conjugate. So this is the so there, suppose there is a function fx that is equal to half x transpose qx. So then we need to find out the conjugate function of fx. So there is just maximum of y transpose x minus fx. So that is shown here, how to find out the conjugate function of fx. So then fx is equal to q root x, then f double dash x. So how to find out f double dash x? So for the q root x. Yes. So then week 7, week 6, sorry, week 6. So uh, so this is the beamforming optimization problem. So these are the applications of convex optimization problems, convex optimization problems. So first problem is that this is a normal beamforming with no interference. So this is a SIMO channel, single input, multiple output. So this is the only one transmit antenna, and there are L number of receive antennas. Then there are L number of equations, received equations. Y1 equal to H1x plus N1, Y2 equal to H2x plus N2, and so up to YL equal to HLX plus NL. So that means y, if there is a vector y which will contain y1, y2 dot yl. So then y is equal to h into x plus n, where h and n both are vectors. So then the beamforming vector means at the receiver end we will do something so that uh, signal power is optimized. I mean the noise power is minimized. That means SNR, signal power to noise power, that is maximized. So that is the optimization problem. So that is done here, minimizing the noise power subject to y transpose h equal to 1. So this is the optimization problem, and if you solve the optimization problem, you will get the uh, the optimal beamformer or vector, that is equal to h by norm h square. So this is the optimal beamforming vector, and this process also is called maximal ratio combiner. Okay, so that is the name. Then for the beamforming with interference, so for that case, there are two number of antennas are there. One is the desired antenna, another one is the interfering antenna, and there are L number of received antennas there. So for the optimization problem, here will be one more. Uh, 1 second. Yes. So for the optimization problem, we need to minimize W transpose RW, where R will contain noise part as well as interference part. Okay, so that is the optimization problem, and such that subject to Y transpose H equal to 1. So ultimately, we are getting W star equal to R inverse H divided by H transpose R inverse H. So if you put R is equal to identity matrix, then you will get itself this H divided by mod H square. So that is here the same thing for the no interference case. So then zero forcing beamformer need to, so here the after, so we don't need to change the objective function itself. We will, for the interference case, actually we will just uh, make another constant in the constant set. We will take one another constant so that the interference term is zero. So the objective function is as same as minimizing the noise power only. There is no interference in the objective function, but in the constant set there is one more constant y w transpose g is equal to zero, which will take care that interference is zero. So that is done here. Then so this is a robust beamforming. No perfect channel information at the receiver. There is a channel estimation error. So this is the solution, and the derivation is shown in the professor's lecture. There is a lengthy derivation, and these are sample problems. Find the Hessian. So this is the x, and so how to find out the Hessian of this x is square divided by y. So this is shown here. Then so we need to show that if this function is convex or not. So it's a greater than is a positive semi-definite matrix. So it's a convex function. Then for this case x1 and x2, for this case you can check that this is Hessian is not positive semi-definite. Hessian is so for the Hessian the eigenvalues of the Hessian matrix is plus minus 1. So it's not positive semi-definite matrix. So if f of x1 comma x2, so that is not a convex function, not convex, not concave, nothing, because it eigenvalues are plus 1, also minus 1. If those are only positive, I mean greater than equal to no, if those are non-negative, then we can say that is a convex function. If those are non-positive, then we can say that this are, I mean the function is concave function. But here both positive plus negative both are coming. Then B here, so how to so B here for AW channel with SNR P by sigma square gamma is Q of root gamma. Prove that. So how to find out? So this is a lengthy process. So just for the clarification we have done in the class, and if x is equal to this thing, find the Hessian. So same question. So we need to show that this function is convex or not. So that is done here. It's a lengthy question, and every norm in R power n is convex function. That is also one observation. Where p is greater than equal to g greater than equal to 1. Maximum of x1 to xn. This is also a convex function. So that is proof is here shown here. So then week 7. So this is a generalized inverse of matrices. So pseudo inverse, I have shown that for the least square problem, pseudo inverse is coming. So this is a generalized inverse. Suppose there is a matrix which is a rectangular matrix, and how to find out the pseudo inverse or generalized inverse of that matrix. So there are no, from normal process there is the B is so suppose A is of dimension m cross n, then its pseudo inverse B is will be of dimension n cross m, and if four conditions should be satisfied. AB is Hermitian, that is AB Hermitian is equal to B Hermitian, A Hermitian is equal to AB, and BA will also be should be Hermitian, and AB is equal to A, and BAB is equal to B. So then B is called Murray-Penrose pseudo inverse or generalized inverse. Uh, okay, so and is denoted by A dagger. Then how to find out pseudo inverse? General process. So suppose there is a matrix A of dimension m cross n, and its singular decomposition is U sigma B Hermitian. Then so we'll form another diagonal matrix sigma 1 that is equal to D inverse 0 0. And then B is equal to B sigma 1 U Hermitian, that is always uh, pseudo inverse of that matrix A. So for any matrix A, we need to know the singular decomposition, then we can find out Murray-Penrose pseudo inverse. That is the process. So least square problem. So once again the least square problem, Ax equal to the B. Then there are okay. So its details about least square. Detailed discussion. So ultimately, we need to solve the normal equations. the normal equations are A transpose Ax equal to A transpose B. If A transpose A is invertible, then the solution least square solution is A transpose A inverse A transpose B. So there is the least square solution. So these all things are there. So these are now some definitions: global minimum, local minimum. For the point x star to be a global minimizer of a function fx, if value is minimum at x star for all, I mean for all values of x. Local minimum is there is some other constant that in this area this should be minimum. So that condition is that f minus x star is less than epsilon. There, okay. So this is a local minimum definition, and this for the vector. So there are two types of optimization problems. One is unconstant optimization problem, another one is the constant optimization problem. For the unconstant optimization problem, there will not be any constant set. There is not be any constant set. Uh, and for the constant optimization problem, there will be some constant set. Uh, so for the unconstant optimization problem, so we have FONC, first order necessary condition, second order necessary condition, and second order sufficient conditions. So for the first order necessary condition, it's saying that a point extra is a minimizer or maximizer of a function fx only if f star f dash extra is equal to 0. That means only it means in the reverse way. That means if f dash x equal to 0, then if f dash extra is equal to 0, then extra will oh, sorry. If extra is a local minimizer, then f dash extra is equal to 0 actually. So in that way. Then in the second order sufficient conditions, we need to check the double derivative. That means if double dash extra is 0, is positive or not. If it is less than 0, so if f double dash extra is less than 0, then extra is a maximizer. Uh, okay, if that is greater than 0, then extra is a minimizer. Okay. So these are the sufficient conditions. Then for the vector case, everything will be same, but for the vector case, double derivative will be replaced by Hessian. Same for the convexity check also double derivative will be replaced by Hessian. For the first order, second order necessary conditions, those conditions, the double derivatives will also be replaced by Hessian. And then convex optimization problem. Oh, these are the reference books. Okay. Uh, so so in the convex functions are generally there are many convex functions, but generally in this optimization various optimization books, their convex function will be one form is linear form, and another is affine function and quadratic function. So only after second order you will get many problems. There are other convex functions also. So okay, so then local minimum is a global minimum for the convex function. So how convexity is necessary to check? There is no relation. Is there any relation between convexity and optimization? Yes, there is relationship. There is a relation because if a function is convex, then its local minimum will also be a global minimum. And other advantages are that so the point satisfying gradient of fx equal to 0 is a global minimum, and if two points satisfies
Sir,
gradient of x equal to 0, then the function value at those points will be equal. So that means for the convex function we don't need to go and check second order conditions. Just the first order conditions are sufficient to say that
one
the
doubt.
function is.
If x is there, it is in a linear program. If x square is there, it is a quadratic. What is the general form for second order cone program, sir?
Oh, for convex function. No, actually, so I don't know actually. So these are so yeah, I don't know. I have to see.
Okay, sir.
But you can, yeah, yeah. That's actually that is also a convex function and convex optimization problem. Actually, Professor has taught, right. So that is not mentioned here. So yeah, okay. So the point satisfying gradient of fx equal to okay. So okay. Yeah. So For the convex functions, just yeah, for the convex function, just first order condition is itself sufficient. That means only gradient of, if you solve the gradient of x equal to 0, then that will give the solution of your optimization problem. No need to go to and check Hessian and positive semi-dependentness. Those things are not required. And for the constant optimization problem, there is also one more constant set, and we need to check that that set is convex or not. There is the one more constant. These are the equality constant, and for the equality constant case, uh, what how to take the FONC? These are written here. Uh, it's a lengthy process, and SONC and SOSCs. So, for the equality constant case, extra is a, so okay, for the inequality constant case, that is the, that will be general. So I will go to there and I will talk about there. So inequality. So in the next slide, in the next lecture. Okay. So these are the, I think, on question of beam forming question. Just putting those formulas and putting those values, you will get the solution. And so there are three questions. One is zero forming, zero forcing beam forming, and then this beam forming with no interference and beam forming with interference. Three questions are there. So we just putting those values. Then lecture 8. So this is the okay. So for the equality constant, sorry, for the inequality constant case, this is the normal general case. So for the inequality constant case, and there can be equality also. This is the KKT we need to check. Okay. So KKT conditions are conditions are like that. So we need to minimize fx subject to hx equal to 0 and gx is less than equal to 0. H is a m cross 1 vector. Yeah, so H is a n cross 1 vector. Yeah, H is a m cross 1 vector and G is a p cross 1 vector. So then suppose extra is a regular point. So that no need to go through regularity now. So that means this suppose there is a vector lambda which will be also m cross 1 and another vector mu is, who is also m p cross 1. So then gradient of fx star plus jh x star plus lambda star jg x star into mu star is equal to 0. That is the KKT equation, one equation where this JH and JG will be gradient of all the H and all the G's. Then H will be a matrix which will take gradient of H1, gradient of H2, gradient of H3, dotted gradient of HM, and G also same way JG. So this is one. So this is one equation in the KKT condition. Another equation is the nu star transpose G extra is equal to 0, additional constant. So that means suppose there is one example. So it will be clear now. So to minimize the function fx subject to hx is equal to 0 and gx is less than equal to 0. So this optimization problem. So the KKT conditions are gradient of fx star plus jh x star lambda star plus jg x star mu star is equal to 0 and mu star is greater than equal to 0. Mu star g x star is equal to 0. H x star is equal to 0. G x star is less than equal to 0. And here there is one example problem how to solve this uh, optimization problem. Okay, and why only first order conditions are written here? Because in this context, in this course, we'll only we'll only deal with the convex functions. So first order conditions are itself sufficient. So that's why no need to go to the second order condition. So that's why this is a lengthy process how to solve problems. So second order condition no need to go to now. So this is a MIMO beamforming. So MIMO beamforming, the solution is that this at the receiver the beamforming uh, uh, vector is that eigenvector corresponding to the maximum eigenvalue of H transpose H. So inverse of pilot match. So these are there is one. So there is one matrix is that 3 cross 2. Inverse of that matrix is equal to pseudo inverse. And if you check that this matrix is the full rank matrix, that is rank of P is equal to 2. Then P transpose P will be a 2 cross 2 matrix. And that rank of P transpose P will also be 2. That means P transpose P is invertible. That means inverse of P transpose P exists. So then we can then P dagger that will pseudo inverse of P will be P transpose P inverse P transpose. That is written here. We have found out the P transpose P, then P transpose P inverse, then P transpose. So this is the pseudo inverse of P. Okay. So consider the least square problem. This is a least square problem. Then this is a solution. We just proof already done earlier also. So then lecture 9. So these are for complex optimization problem representations. There are two forms. One is canonical form, another one is epigraph form. So canonical form is normal form. Okay, what we have written up to this minimizing G0 x subject to GIX less than equal to 0 and AJ transpose x equal to BJ. And for the epigraph form, minimizing, so there will be those objective function will go to one constant itself and we'll just minimize another t actually. So that means it's same minimizing it's same as minimizing t subject to g0 is less than equal to 2 t and all other constant will be same. So this is just a epigraph form. And dual problem of convex optimization problem. So dual problem is that uh, dual function definition. Uh, Suppose the Lagrangian of suppose there is a function fx, we need to find out the dual function of fx. Okay, so uh, then for that case, first we need to calculate the Lagrangian of that Lagrangian of x. Lagrangian is equal to fx plus lambda transpose hx plus mu transpose gx. Okay, then the dual function will be infimum of this Lagrangian with respect to x. Okay, then so there is a dual function. Then the dual optimization problem is that so the minimizing the primal optimization problem was that minimizing fx subject to hx is equal to 0 and gx is less than equal to 0. Now the dual optimization problem is maximize that dual function q lambda mu subject to mu is greater than equal to 0. So that is a dual optimization problem. And strong duality relationship is that uh, uh, the solutions of dual and primal optimization problems will be same. There is a strong duality relationship. Linear program. Uh, so linear program. So for the linear program problem, L transpose maximum. We need to minimize. Sorry, we need to minimize C transpose X subject to X equal to B and X is greater than equal to 0. So then we can find out the dual problem of linear program problem. That is done here. In the assignment, maybe you had some questions on dual optimization problem of LPB program, linear program. So then compressive sensing. Suppose there is a matrix. So the system model is like that. Okay, I will go to later. So yeah, so this y is equal to for the compressed sensing case, the system model is y equal to phi x, where phi is called a sensing matrix and x is a sparse vector. Sparse means there will be so many zeros in the vector x, and y is called the observations. So so how to find out the x, the sparse vector from this system model? So that is the question. So normal optimization problem is that minimizing the L0 norm. L0 norm is that will count the non-zero elements in that vector x. So minimizing the L0 norm subject to y equals to phi x. Then combinational. So it will. So but the thing the problem is that this optimization problem is not convex optimization problem. So Is a non-combinatorial problem. So solving is very difficult and it will take a high complexity. Okay, so there is the NP hard problem. That's why we need to go to some other approach. So that may not be that may not be optimal itself. Like that, this OMP, orthogonal matching pursuit algorithm. This is a greedy algorithm. This is a very simple and low complexity algorithm, but that will not give the optimal solution. But its complexity is very less, too less. So so what is the OMP algorithm? It's written here. So this is the suppose in your assignment or in your paper you have one question how to that find the this sparse vector. So then you need to go through this OMP algorithm. Okay. So then this suppose R is equal to Y. So so this is a process actually. Y equal to phi x. You need to solve. You need to find out x from this Y observations. So at the beginning, you will set residue R is equals to Y, and suppose set A's will contain zeros at the beginning, and A's will be null set at the beginning, and A will also be null set, null matrix at the beginning. Then this is the the convergence rule. Then you will find out lambda is equal to R transpose phi, absolute of R transpose phi. So that will be done. Then you need to find out the maximum of the position of the maximum value of lambda. So that is found out here in this val. So this index will take the position of the maximum value of lambda. The S will take that index. Okay. So then A will be some other matrix that will contain only those columns of sensing matrix. Okay, then X is the A dagger Y. A dagger means pseudo inverse of A into Y. Uh, R is equal to Y minus X. Then residue equal to Y minus X. So at the end, I will see the chat questions. So uh, so then so this is the process. Yeah, so this is the process, and in the one question, I will show how to solve the uh, uh, how to find out the sparse vector using OMP algorithm. And L1 by L1 minimize non minimization also you can solve. You can minimize the L1 norm subject to y equal to phi x. So that will be as this L1 norm is a convex function, that may be easier to solve. Okay. So epigraph of this thing uh, is written here. Program problem can be solved. Consider two vectors, find out the orthonormal vector. So this is just a ground spin orthogonalization. Then maximize x transpose x subject to this. This just yeah, this question somebody asked last class. So this is just solution how to find out what is the derivation of. So I have told that this maximization of x transpose x will nothing but the maximum eigenvalue of A, but the solution is written here. So yeah, so then this is the distribution. So this is the things as okay, L0 and L1 norm. Yeah, for the composite sensing problem, which norms should be minimized? L0 and L1 norm should be minimized. So okay, consider the MIMO channel matrix. Receive beamforming is equal to okay. So then week 10. Yeah, so this is the question. So consider the sparse signal estimation problem. This thing, then solve this by using orthogonal matching pursuit algorithm. So so then so this is the just yeah, example problem. So phi is equal to this matrix. Now at the beginning we need to set residue R is equals to y is equal to 143. Okay, the lambda is equal to absolute of R transpose phi. So that is done here. Absolute of R transpose phi. R is this 143. So 143 into phi. Then absolute of these things are written here 445,373. So you can check that in the lambda 7 is the maximum value and that is occurring at the fifth position. So S will take 5. Okay, then A will take fifth column of 5. So that means 011. So here you can check 1 2 3 4 5 0 1 1. So then X is just A dagger Y. In this case, in this step, X is coming out 7 by 2. It's just a scalar in this step. Now residue is equal to y minus ax. that is equal to this thing. Now we will find out lambda again. So lambda is equals to absolute of R transpose phi. So that is coming out this 0.5, 0.5, 1.5, 0.5, 0, 0.5. So out of this, 1.5 is the maximum and it is occurring at third position. So now SU will contain 3 also. So earlier it was 5, now it's 3. So SU will contain 3, 5 now. And A is now a matrix which will contain third and fifth column of 5 columns of 5. Third column is 1 1 0 and fifth column is 0 1 1. Okay, so that is equal to A. So A is equal to 1 1 0 and 0 1 1. Now X is equal to A dagger Y. Now X is coming as a vector 1 3 1 3 vector. Now R is residue is equal to Y minus X. Again you find out the residue. And in this case it's coming out 0. Oh, then it's converged already. No need to go to further. So the solution is that maximum positions are 3 and 5 and values are 1 and 3. So now X is a vector of 6 comma 1, 6 dimensional vector. Out of 6 elements, only third and fifth positions are non-zeros and their values are 1 and 3 respectively. Okay, so now find the dual of problem of the following optimization problem X transpose X. So that is the dual problem. Just find out the Lagrangian and minimizing Lagrangian. Okay. Now, this is the frequency selective channel power allocation. So optimal power allocation problem is also there in the assignment. So that's why it is the derivation of OFD optimal frequency division multiplexing case. So for that case, what should be the optimal power allocation allocation? Okay. So this optimization problem is the maximizing the capacity subject to summation of Pi is equals to P total. P total is the total power budget and Pi should also be greater than equal to 0. So the solution is coming out like this only. Choose so Pi star is equal to 1 by lambda prime minus sigma square by mod Hi square. Power plus, this is the plus sign. Plus sign means that will take maximum of that value comma 0. If that is negative, the inside value is negative, then it will take only 0. If it is positive, then it will take that value itself. Then so this is the optimal power, and for the MIMO channel also the solution is kind of like this only. So this is also optimal power, and we will solve two questions. We will solve questions on MIMO channel power allocation. So the solution is like the Pi star is equal to 1 by lambda minus sigma square by sigma square plus uh, so later, and this lambda should be chosen to meet the equality power constant, that is summation of Pi is equal to P total. So there is a one question problem. P total is equal to 2. Total power budget is 2 and sigma square is equal to 16 and sigma is 2 and 4. So there are two singular modes. Okay, two singular modes. One for the one mode, its singular value is 2 and another mode singular value is 4. Now we need to find out the P1 star and P2 star. Okay, the optimal powers for two singular modes. The optimal powers are like that 1 by lambda minus sigma square by sigma 1 square. That means sigma square is 16 divided by 4. That is coming out 1 by lambda minus 4 plus, and P2 star is equal to 1 by lambda minus 1 plus. Now, so this is now left hand side there is one diagram. So here this is singular mode 1, singular mode 2, and for the singular mode 1 is 1 by lambda minus 4. So suppose this is the 4, and then for the singular mode 2 is 1 by lambda minus 1. So the difference between 4 and 1 is 3 itself, 3 itself. But the total power budget is 2. So the 1 by lambda should be between 1 and 4. It will not go beyond 4. Okay. So that is why for the P1 star it is 0. So as the total power budget is very low, the optimal power allocation for the singular mode 1 is 0 itself. But for the singular mode 2, it's 1 by lambda minus 1. Okay. So that means total power budget is 2. So all the power is going to the singular mode 2 itself. So that means 1 by lambda minus 1 is equal to 2 and 1 by lambda is coming out 3. So that means P2 star itself is 2. The power is going to the singular mode 2. Okay. So that means P1 star is equal to 0, P2 star is equal to 2. So then we can solve then week 11. So here One another question on MIMO channel with two singular modes, same questions. Sigma 1 equals to 1 by root 2 and sigma 2 is equal to 1. Then we need to find out the P1 star and P2 star. So P1 star is coming out 1 by lambda minus 2 plus and 1 by lambda minus 1 plus. So the difference between 2 and 1 is 1. But the power budget itself is 8. So it's more than that difference. So we can set 1 by lambda beyond 2 itself. That's why for P2 star it's coming 1 by lambda minus 2 and 1 by lambda minus 1 for the, so for the P1 star it's coming 1 by lambda minus 2 and for the P2 star it's coming 1 by lambda minus 1. And sum of these two is itself is equal to 8. That means 2 by lambda minus 3 equals to 8 and 1 by lambda is equal to 5.5. Then P1 star is equal to 5.5 minus 2, that is 3.5, and P2 star is equal to 5.5 minus 1, that is 4.5. So these are the solutions. So there is one another question only to go because this type of question already solved last class. So consider OFTM symbol. So similarly for the OFTM also same questions. HI is written here and then solving same way. This is the L0 norm. L0 norm is 3 here because there are 3 non-zero elements there in the vector X. And sparse chain estimation problem. Same problem I have shown it here again using the OMP orthogonal matching partial algorithm. And okay, this is the solution. And then week 11 and done, week 12. So in the last class, uh, the afterwards also, this is the semi-definite problem question. So the definition of semi-definite problem already Professor Tolai have just followed his lecture. So this is the semi-definite problem. Then for the HDB for the ML detector, that is coming out just derivation that is coming out equivalent problem. Second is coming out. Uh, yeah, this thing. From this we can estimate S, where S is equal to root lambda 1 Q1 root Q1, where Q1 is the eigen vector corresponding to the maximum eigenvalue lambda 1 of S. Okay, so capital S. So this is the just derivation. So then semi-definite problem. So this is just from the basic definition of what which problem is a semi-definite problem. So this third option is correct, and optimal problem is can be formulated as a linear program problem, and then this is also linear program problem. Then uh, one has given that question. A is equal to this matrix, then find out the x transpose x, maximum of x transpose x. That is the maximum eigenvalue of A. So that is maximum eigenvalue is coming out 20. Okay, the answer should be 20. Uh, if it is minimum of x transpose x, then that will be minimum eigenvalue. That will be 10 for this case. Okay, so that's all for today. Now let's open the chat. Okay, so one is asking how to distinguish out uh, distinguish out quadratic, linear, and second order cone from a given example. Actually, this is just a definition, right? For the second order cone. From the definition itself, you can differentiate, right? From quadratic to second order cone itself. Sorry, quadratic or linear or second order cone. And minimizing x2 and minimize x infinite. What is the this how to minimize x2? Okay, minimizing x2 norm means it will be x. So x2 norm means you can minimize x2 norm square. Okay, that means minimizing x transpose x. Okay, x transpose x. If you want to minimize, then that is a quadratic problem. So that means to differentiate it. It's a lengthy process, but it's a simple process. Already professor has also done. So X transpose X is, you can write it down. So minimizing X2, that will minimizing X2 norm square, that is minimizing X transpose X. So okay, so then the Lagrange X plus some constant is there, lambda of something. Then if you then you can differentiate it, okay, and make it zero equals to. Then that is suppose you can write down X transpose IX, and already we have solved X transpose QX those solutions. Q is equal to I in this case. So like that way you can solve. That is the same process actually. Okay, and X infinite norm. X infinite norm is that is the max. Okay, how to solve the X infinite norm then? That will be solved. Mm, that is a convex function, and so no, in this way you can solve. So there is this way you can't solve it. So correct. Maximum is mod of xi. So yeah, so you can't derive differentiate it mod of xi. So but other way you need to check it. You need to find out the this infinite norm. Okay, so the infinite norm itself, so is a so in the L2 norm there is no maximum, there is no maximum itself. So minimizing the L2 norm it's okay, and in the maximum norm definition itself there is one maximum. So there is one optimization problem itself in the maximum in the infinite norm definition. Okay, I mean you need to do it some cleverly something. Okay, if you have any questions, so okay, yeah. So that's all for today. Yeah, and this is the last class. Thank you. I will upload this all the lectures in the folder today itself, so that you can it can be ready for the exam. Okay. Best of luck for your exam. Thank you and all the best. If you yeah, in the mid way, if you have any question, you can mail me, so I can write down my mail IDs. Suppose immediately you need some help, I will be available every time. So you can mail me anytime. Okay. So I am writing again my mail ID. If possible, I will try my level best. NILA, one second. NILADRI, NILADRIH, C dot C dot IN, NILADRIH. Yes, correct. So yeah, I have given my mail ID. So please mail me. And after the exam, for the feedback, you can mail me. Okay, here if you feel that I have taught. So I should teach in this way or different way. You can mail me, so that will be helpful for me actually also. So later, yeah. So this is my first year session. Okay, thank you, and yeah, for the whole session. Thank you. Okay, bye. See you. Bye.
Sir, can you solve assignment 11 problems, sir?
Okay, so you told me one question that is classified, regularized classifier last day you were telling about. Okay, yeah, that question I solved. That is just definition itself. Professor has done in the class, right? That regularized classifier definition. That exactly is taken is the question in the assignment. Okay, that summation of something plus lambda of u minus ui minus vi. So you can check that professor itself done has done same thing, same is just definition. That classifier question. Any other question you want? That day we are solving, right?
Okay,
Last
sir.
day, yes.
Okay, thanks.
Okay. Thank you. Thank you for joining. Bye.
Sir, how can you